Hello, I'm going to try to explain a little of this stuff here from section 2.4 about mechanical vibration, just so that when you look through the book, you'll have a good sense of what's going on. So here's what's happening here. Here's a little setup here. I drew this picture here. So we have a spring here, okay? That's a very bad picture of a spring. And here's our object that has mass m, okay? And so m is the mass, and we have this frictionless surface here. So you imagine this is a frictionless horizontal plane. So we're going to use assume Hooke's law for the spring. That is that the force of the spring is going to be negative k times this distance x, where the distance, where this point here is the equilibrium point. So if the object wanted to stay at rest, it would stay there. So if the object is pulled to the right, then x is positive, so the force would be pushing towards the left, and we're assuming k is positive as well. So that's the force of the spring. Then we have the next force acting here, F sub r. That's the damping force that we're going to be considering. So we have this object, this thing here. Okay, this is like a shock absorber, or a dash pot, right? So think of it as a shock absorber, and what it does is it exerts a force on our object that is given by the following expression. It's minus c times dx dt. So if the object is moving dx dt, right, it's going to be exerting a force. So if the object is not moving, it does not exert a force. So if everything is at equilibrium, all of the forces so far are zero. Let's see, what else do we have here? Okay, so then there might be some external forces. For example, we might have, perhaps in the future we'll have something, pushing this this object back and forth. Okay. So then what we have here is the total forces. You add up all the forces, you get the external forces, and then you have Newton's law of motion, is that the mass times acceleration has to be equal to these forces. And so if you write that down, you get this expression right here, and which gives us this nice differential equation that we would like to think about right here. Okay, so there's a number of cases we want to go through and see how that relates to our solutions. The first one we call this free undamped motion. And that's when c is 0. In other words, when c is 0, then then it's as if this isn't here, this dash pot. So the object just moves and oscillates based upon the forces exerted by the spring. Okay, so we've seen differential equations like this. We define this omega sub 0 to be our spring constant divided by the mass, actually the square root of that, and that allows us to just write down this nice form of our differential equation. All right? And then using techniques that we've studied, we see the solution here is given by this expression here, where we get x of t is some constant times the cosine of omega 0 t plus b times the sine of omega 0 t. So what we do is we to look at to study the dynamics of this, what we do is we usually let this c be the square root of a squared plus b squared, and we define the cosine of alpha to be the a divided by c, and then the sine of alpha to be b divided by c. And the best way to understand this is that, you see, given any point, cosine theta, sine theta, you get a point on the unit circle here, right? So the theta that we're talking about is the angle that is formed here, right? So theta can be any angle between, actually we're going to take it between 0 and 2 pi, okay? Well, if you make these substitutions here and use the properties of trigonometry, you can rewrite our solution in this nice form here, that x of t is actually this c times the cosine of omega 0 t minus this alpha. And this should look familiar from trigonometry, essentially, that you have c is the amplitude of this function. Omega 0 is the circular frequency, and this alpha is the phase shift Here, let me try to make this. So I have this little program here that I sort of programmed is an exaggeration. I basically have this this thing that graphs things. So up here you're seeing my cosine of 2t minus pi. So that would be my solution. And as you can see, and as you would expect, here it's called y, and here x is called t. But here's the motion of our object. It would oscillate back and forth around its equilibrium. Okay, and just to show you what these things are, for example, I'm going to just make pi equal to 0, the phase shift, right? And if I graph that, what you're looking at is just the cosine. So it's perfectly, it's not shifted away from the cosine, the graph of the cosine. It's the cosine of 2t. So let's subtract pi again and shift it over again, as they say, right? So I'm going to shift everything over by pi, right? The other direction though. And now let's take a look at this 2. What this corresponds to is, here, I'll make it equal to 1. So this idea of the circular frequency, if I put a 1 there, notice what happens is that you undertake one complete cycle in exactly 2 pi. In other words, once around the circle, you get one cycle of the function. Now, if I put a 2 there, right, coefficient right there, 2, then what you notice happens is that you sort of double that. So you go around the circle once, so you get time. In other words, if time goes from 0 to 2 pi, then the function does 2 complete cycles, right? 1, 2. Okay, so that's the situation if there's no damping. So next one, we have a free damped motion, right? Damped as opposed to undamped. So what that corresponds to, the free means that there's no external forces, right? But the damped means we have our C greater than 0, and that's basically putting a shock absorber on the end. Well, in that case, we have the differential equation then has this middle term in here, and then we want to make a few other substitutions to rewrite it, as you see here. And if you do that, you can rewrite the differential equation this way. And then we get our characteristic equation, which now you know could have could have one root, 2 real roots, or 2 complex roots, okay? And each of those situations now we want to study. So here's just some, you can write this down. We make some substitutions. We have the roots of this, R1 and R2, then are in this nice form here, right? And then if I look what's underneath the radical, in other words, if I look at the discriminant, this quantity here, it is right here. So the critical point for that discriminant is this we call C critical, and that's when the numerator of the discriminant is 0, okay? So then we can solve this differential equation. We get 3 different types of solutions. We get when the critical, when C is less than the C critical, then our solutions look like this, okay? When we get the exact critical, then our solutions look like this. And when C is greater than the critical value, it looks like this. Now I want to pull up this, you can solve that using the techniques that we've studied, but I want to show you what that looks like here inside of our, our stuff here. Let me see if I can get my proper, here we go. That's what I'm looking for. Sorry about this. There's my little guy back there. Okay, here we go. All right, so here it is. So here's the undamped situation, right? And here's an example of the, let me click this off here. Here's an example now where we get a solution of the form, the last form, when we're beyond the critical point. And notice that when we're beyond the critical point, the damping is such, right, that it doesn't allow the spring to actually reach the equilibrium. It just kind of approaches the equilibrium, okay? And if we're, the next case is when we're damped. This is the case. Notice that we have this linear factor. That's the case when we have when we have exactly C critical. In that case, what happens is that the particle or the object can go past the equilibrium once, and then it approaches the equilibrium value as time goes to infinity. So those are the two cases when we had the C is greater than the C critical, and the case when C is equal to the critical damping. Now, the kind of interesting case is when C is less than the when C is less than this. Oh God, I'm sorry. When C is less than C critical, then we get an interesting situation right here, and this is just an example of a graph. Notice how here what happens is that the spring starts, and you can imagine it. X comes back, goes past the equilibrium, comes back, past the equilibrium, bam, 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 and it just oscillates like this. So that as the limit as t goes to infinity, the object does eventually come to rest at the equilibrium, but it swings back and forth an infinite number of times. So hopefully this helps you. There's a couple of questions that you'll go through all of the calculations and write down some solutions. But I hope this gives you some sort of an intuition as to what the relationship between these the damping constant is and then the dynamical behavior of the system. So, all right, thank you.